Here's the lecture notes from section 7.4, having to do with the lengths of curves. Let's start this out by doing a little exploration. I'd like to find out what is the length of the sine curve from x equals 0 right here to x equal 2 pi right there. Here's an estimate. How about I draw the line from there to there, and there's an estimate of the arc length. My first estimate is 2 pi, or approximately 6.28. And you're like, well, that's great, but that's not a very good estimate. And I'm going to agree with you. I'm going to say we could probably do a better estimate. A better estimate might say, hey, start at this green point, but then go to this green point. And that hypotenuse is a reasonable estimate of the curve that starts and ends at that same point. And I think we can find the length of that hypotenuse. I know that this is 2 pi, that this is pi. This would have to be pi over 2. And so I have a triangle there. This hypotenuse, I'll call h, is the square root of pi over 2 squared. And then the height of this triangle is 1. So how about of 1 squared? And so that could be a pretty good estimate. Let's go to the calculator and find out what that value is. That value is equal to. So here's my calculator. Start a new document. Have a calculator page, and let's go ahead. Square root of quantity. Let's make this fraction. Pi over 2. Let's go ahead and get out of that parentheses. We'll square that, and we'll add 1 squared on the end of that. We get that value. I'd rather be interested in the decimal representation, but 1.962. Okay. This is 1.962 approximately. Oh, wait, but there are 4 of those hypotenuses. Okay, so let's say that the arc length would actually be 4 times this approximate value, 4 times this value. So we're coming up with about 7.448. 7.448. It's longer than the 6.28 that we started with. And I could say that indeed, we'd say that that is reasonably more accurate. But then we said, well, could we be even more accurate? Could I take this and find the arc length of the hypotenuse of that triangle, and then find the arc length of that triangle and get an even better estimate? Well, let's try that. Let's call this hypotenuse H1. We'll call this hypotenuse H2. Let's find out what H1 is. H1, it has a triangle. Since this is pi over 2, this would have to be pi over 4. So the pi over 4 squared there. And then height of this would be, well, how high, how tall is the sine curve at pi over 4? I think that'd be root 2 over 2 squared. So there's another good estimate. Let's go ahead and throw that into the calculator. Square root and parenthesis fraction pi over 4. Let's square that, and let's add to it, again, the value of sine at pi over 4, which is root 2 over 2. And of course, we'll need to square that as well. All right. Now I want the decimal approximation. 105, 1.057. 1.057. All right. And then what about H2? A good estimate of that little hypotenuse would be something like, well, it's still pi over 4 wide, or in its base, and its height is that root 2 over 2, and then this was 1. So how about that height of that little right triangle is 1 minus root 2 over 2 squared. How about that? I think I can just edit this and just say 1 minus that and get a reasonable estimate, 0.838. 0.838. And well, it seems to me like we'd have 4 of those H1s and 4 more of those H2s. So how about our length estimate? Our length is approximately, it should be approximate as well, 4 times H1 plus H2. All right. So 4 times, oops, parenthesis, this number plus that number. All right. Okay. 7.58. 7.58. And we can see that every time we do this, we're getting a little bit bigger because our hypotenuse, the hypotenuses are getting closer and closer to the real arc length. Now, question is, instead of all this fooling around with breaking it into subintervals and doing that work, could we find an expression that gets us there, and not just an estimate, gets the arc length? Well, let's follow this idea. The triangle that we were using the hypotenuse on has some change in x. I'll call that change of x dx, and some change in y. I'll call that change of y dy. And that makes the hypotenuse dx squared plus dy squared. And that is a pretty good estimate for a very small piece of arc length. But here's our problem. We don't want a very, very small piece of arc length because dx and dy are infinitesimally small. We want the sum of all those little pieces of arc length. And while we could recognize that it's going from A to B for our arc length, this doesn't look like our normal integral. There's no sort of dx or dy out there. Well, what would it take to get a dy or dx at the end? Well, why don't we multiply by dx over dx, which is like multiplying by 1. And then let's say we take that bottom dx and we bring it inside the square root. And the act of bringing it inside the square root makes it a squared. Just like the action of taking out of the square root takes the square away. And if I distribute that dx squared, the 1 over dx squared across both of those terms, I get the integral from dx squared over dx squared plus dy squared over dx squared and a dx at the end. Or I get my arc length formula from A to B of the square root of 1 plus dy dx squared dx. Now, how does that play out with this particular problem? Well, we were told that y is equal to the sine of x. Therefore, dy dx is equal to cosine of x. Therefore, the arc length from 0 to 2 pi is the square root of 1 plus cosine squared x dx. We're not going to go into how to find that integral exactly, but we will let the calculator do the work. So one more time to the calculator. How about the integral from 0 to 2 pi of the square root of 1 plus cosine of x squared dx. And there we have it, 7.640. 7.640. And we're going to note, of course, that's a little bit bigger than our other estimates because we're no longer having those little gaps between the hypotenuse and the real curve. Slight note here, let's just switch over to the red marker to note that in this process where I multiplied this integral by dx over dx, I could have, at the same point, have chosen to take the dx squared plus dy squared and multiply it by dy over dy. And if we did that, then we end up getting the integral of, not the integral of integral, the integral of the square root of dx squared over dy squared plus 1 dy. And then, of course, if that was the case, we would be going from not a to b in the x orientation, but rather c to d in the y orientation. Let's summarize this with our definition. If we have an arc length that's going from AC to D, sorry, a piece of arc, a piece of curve that goes from AC to BD, and A is greater than B and C is greater than D, then the arc length can be thought of as this integral from A to B with that integrand as we talked about earlier. If y is a smooth function on x, and we could do it in the y orientation if x is a smooth function on of y. What do we mean by smooth? Means, I'm going to say that it means that dy dx, in this case, not undefined. Okay, and in this case, it means that dx dy is not undefined. It means a little bit more than that, but we're really not going to get into more of the detail. You're going to see in the practice problems situations where they ask you to get an exact length. Let me just tell you right now, most of the integrals created by the arc length formula are not doable by hand. They're just, the integrands are just beyond our skill set, and some of them are simply just not doable. If they ask you to find the exact length, it means the integrand is, the antiderivative is findable. And these problems tend to be very, very contrived. So, for example, if y is equal to 4 root 2 over 3 times x to the 2/3 minus 1. All right. Well, let's take that, find that derivative, dy dx. So I've got 4 root 2 over 3 multiplied by 3 over 2 times x to the 1/2. Well, how about that? Look at how that ends up just those 3's cancel, this 2 cancels with that, 4 and gets a 2. It ends up we've got 2 root 2 x to the 1/2 as our derivative. That means our arc length, and by the way, quick check, is that derivative, does it exist everywhere? And it does. The arc length from 0 to 1, square root 1 plus 2 root 2 x to the 1/2 squared dx, or the integral from 0 to 1 of the square root of 1 plus, and I believe the square of 2 root 2 is 8 x dx. Okay, well, this looks like a candidate for a u substitution. 1 plus 8x. du, therefore, is 8 dx. Therefore, 1/2 du is equal to dx. My rewrite becomes the square root of u, 1/8 du, and let me make sure to change the limits of integration. Instead of from 0 to 1, it is now 1 to 9. So how about 1/8 antiderivative of u to the 1/2, make the exponent 1 bigger, multiply by the reciprocal from 1 to 9. So that'll end up being 1/12 u to the 3/2 is evaluated from 1 to 9, which is 1/12 9 to the 3/2 minus 1 to the 3/2, which is 1/12 9 to the 3/2. Square root of 9 gets 3. 3 cubed is 27. And the 1 to the 3/2 is 1. So it looks like I've got 26 over 12, which reduces to 13 over 6. So highly contrived, and we were able to do this one by hand. This one, I don't think we're going to be so lucky. I'm going to do this in red, because what I'm going to do initially is going to be wrong. I'm going to purposely do it wrong, and we're going to see where it leads. I'm going to just pretend everything is fine. Y is equal to x to the 1/3. Therefore, dy dx is equal to 1/3 x to the negative 2/3. And here I am going blindly towards finding the arc length from x equal -8 to +8 of the square root of 1 plus 1/3 x to the negative 2/3 squared dx. And I don't even think I'm going to be able to find that antiderivative. So I'm going to go right to the calculator. Let's see what it says. Shift plus to get our integration symbol. -8 to 8. Let's go ahead and get that square root. 1 plus parenthesis. And again, it was 1/3. Let's see, x to the power of -2/3. And again, blindly, gotta put that square in there, right there. And let's go ahead and do that interval. That's not what I expect. I got a warning sign there. I got an imaginary number there. That's not good. And why wasn't it good? Why was this wrong? Well, it was wrong because this curve, y equals x to the 1/3, has a vertical tangent. It has a location at 0, which we go through, by the way, where is undefined. Okay, so how would we do this right? Well, let's start with the fact that if y is equal to x to the 1/3, that means y cubed is equal to x. And maybe what I should be looking at is dx dy, which is 3y squared. And therefore the arc length is going to be from -2, a y value, to +2, the other y value, of the square root of 1 plus 3y squared dy. And let's see if our calculator likes that. Shift plus -2 to 2 of the square root of 1 plus quantity 3y squared, close parenthesis, squared, squared, and do this with respect to y. And there we go, 17.261, 17.261, which seems quite reasonable.